And move on to the next speaker, which is Rosa Valenti from the Goethe Institute, Frankfurt, who will give a talk entitled "Is Ruthenium Dioxide an Altermagnet?"
Yes, hello. Okay, so first of all, thank you very much um, for the possibility to present some of our results here in this conference. And what I would like to talk today is about ruthenium dioxide and the question whether this material is actually an altermagnet. This has been a topic of discussion in the last years. And here I would like to present a combined theory and experimental discussion, and then come into a conclusion about this material. First of all, I would like to thank my collaborators in this work, Laura Garcia Gazull, who is a PhD in Frankfurt, Andriy Smolyaniuk, who is at the TU Vienna, and Igor Mazin, who is in the US and the George Mason University, as well as a few experimental colleagues from Würzburg, PSI Switzerland, as well as ISIS at the UK. So as we know, and we had seen already in this very nice talk by Elena, ruthenium dioxide has actually been one of the testbed materials of altermagnetism, since it nicely shows, being a rutile structure, that if it orders, the order should be altermagnet. So that we should have a test case for showing altermagnetism in a material where it clearly, if ruthenium gets a magnetic moment, we do have this kind of configuration. So what do we know about ruthenium dioxide? This material is a material that has been investigated already a long way back, already in the 70s. And I'm showing here, starting with some thermodynamic measurements. So let me start with experiments. What do we know from this material from the experimental point of view? So here what I'm showing is heat capacity measurements from various groups. And as we can see, there is, and these were measurements already done in the 80s and even before that, so that there is no phase transition being observed as a function of temperature. So both in this figure A as well as in this figure B, if we see here the C over T, it's basically, it follows just a linear behavior with no signatures of a possible formation of a long-range magnetic order. And here, in fact, the temperatures are at much higher temperatures. Also, if we look at magnetic susceptibility measurements, here it is for different, considered for different materials, but this is the case of ruthenium dioxide. As one can see, susceptibility as a function of temperature, it follows a completely basically independent temperature behavior, which is what you expect for Pauli paramagnetism. So that basically the system doesn't seem to order. And the same for resistivity. The resistivity behavior is that of a metal with no signature of going into a magnetic phase. Now, more recently, so in 2019, with all this discussion, in fact, all the nice works by Libo, Thomas, and Hyrok came out, there were some experiments, some new experiments on ruthenium dioxide showing, in fact, some kind of magnetism. So here, what I'm showing is resonant X-ray scattering measurements from Zhu and collaborators, where depending on the in and out configuration of the light, they observe a certain configuration. So this is the sigma pi prime, where they find that there is indeed a peak, so in intensity, which would or the one could interpret as the fact that this material is ordering with a very small ordered magnetic moment, and in a configuration which is, as you see, it's really an altermagnet configuration along the z direction. And a second kind of experiments or type of experiments that were also done during those years is neutron diffraction experiments from Oak Ridge. And here what I'm showing is X-ray diffraction, where what they want to show here that if we concentrate on this 100 region, which would correspond to this type of altermagnetic order, in X-ray diffraction, there is no signature of any kind of lattice distortion. However, neutron diffraction seems to observe a peak intensity in this region of the Q vector 100, which would correspond to this kind of altermagnetic order. And if they want to extract a magnetic ordering moment, it would again be a very small magnetization. However, already in this work, the authors are very much considering not clear whether this is magnetism, what they are observing, or some kind of structural distortions, as it can be observed in their magnetic susceptibility measurements. So as we see from this thermodynamic magnetism and neutron resonance scattering measurements, there is some controversy about whether the system is magnetic or not. Here, what I'm showing also is Hall effect measurements on thin films, where they observed by basically considering ruthenium dioxide on titanium dioxide, that going low in temperature, there is the observation of a nonlinear type of behavior in the Hall effect, which was also interpreted as a signature of possible magnetism in these systems. So the question is, there is clearly an experimental controversy with these different type of experiments that I was showing. I am a theorist, so the question is, what does theory tell us? What does the microscopics on this material tell us? And let's see whether we can resolve this controversy. So of course, one of the methods which is very useful to investigate magnetism in metallic systems is density functional theory. And one has to choose, of course, the appropriate exchange correlation functional to describe the magnetic properties of these systems. So because ruthenium dioxide has ruthenium, which where the electrons are for the electrons, one should consider a functional which is just beyond GGA or LDA, in order to include the effect of correlations for the electrons. And one of the functionals that is rather useful for that is what we call LDA plus U or GGA plus U. So now what I'm showing here is the total energy of the different magnetic configurations in ruthenium dioxide as a function of this U, which is basically including more and more correlations effect beyond DFT in the calculation. And energy is a good test, or is a good quantity, in order to tell us about which is the most stable structure in this system, since DFT is a variational theory, and therefore the lowest energy will tell us the most stable configuration. So if one starts the calculation by just increasing the effect of correlations, so this is the energy corresponding to this type of state, as you can see here is the magnetization is 0. So by just increasing correlations, the system wants to be stabilized, or is stabilized in a non-magnetic configuration. So basically when the magnetization is 0, even going to very large values of U. However, if one starts the calculation by considering, just by looking whether you have other type of minima, so at very large U's, there is a region, you see this region here of these crosses, which correspond to a non-zero magnetization. There is this region of U's where the stabilization of the state is indeed an altermagnetic state. So it is an ordered state with altermagnetic order. If we now analyze a little bit more in detail this region where one finds this solution, the state indeed is a state where the magnetic order is a magnetic order along the z-axis that corresponds to this altermagnetic order that was suggested by these two experiments. However, if we look at which values of the correlation we have to put into the theory in order to get into this magnetic order, these are huge values which are definitely not the representative values for the electrons. So that means we are in a very unrealistic region in the theoretical description to obtain this magnetic state. So therefore, by looking at these results, what we decided is then, okay, but we saw that there are some experiments where they seem to find this altermagnetic order. Now, if we look at the density of states, which is also one of the indicators that the system may be unstable towards a magnetic order, in ruthenium dioxide, at the Fermi level, basically, we do have very low density of states, which would be unfavorable to magnetism. So what could be the origin of this magnetism observed in these experiments? So what we did next was, we know that these materials are oxide materials, and oxide materials are very, in fact, it's very, very often that we have some kind of impurities, oxygen vacancies, ruthenium vacancies. This is very often in oxide materials. Therefore, why don't we then analyze what is the effect of having some doping in these materials due to the fact that there are the presence of some vacancies of any time, oxygen or ruthenium. And what one can do in DFT, one can apply what we call the virtual crystal approximation, where the idea is that you do the calculation of the system by considering, in fact, some virtual atom here, which has the charge that you want to describe. So in this case, what we are describing is a doped kind of system. So we are doping the system by considering artificial, if you want, artificial type of atoms. And then we analyze the magnetism of the system. And what I'm showing here, this is again this U of the calculation as a function of number of electrons. And the color plot is the magnetization of the system. And as soon as we put some doping in the system, so basically here I'm showing hole doping, the magnetization starts to raise already at values of U, which are very reasonable for ruthenium dioxide. So that's what we were calling it, the fragility of the ruthenium magnetic moment, that by having some impurities in the system, it may then, in fact, create some magnetism in the system. So that suggests that in some of these considered samples, there may be some impurities. But the story doesn't end here. So then we went back and we joined forces with our experimental colleagues, where they have very good quality single crystals of ruthenium dioxide, as well as thin films up to a thickness, I think, of 10 nanometers. And our colleagues basically performed Newton diffraction measurements on these ruthenium dioxide single crystals. And here what I'm showing is the intensity of the reflections in this region, in this 100 reflection, where you would expect a signal if the material would order. This is in fact the intensity that we see, that they observe no intensity, which is telling us that these samples that they have, that they don't show any Q equals 0 magnetic order, so any altermagnetism. And the question is why the Oak Ridge group was seeing some intensity in this region. The conclusion was that, in fact, in this system, it's very, very, one of the possibilities that could happen in this, by analyzing the measurements, is that you may observe a lot of multiple scattering, and this may falsify the interpretation of your signal. So that was one of the possibilities to understand why in these previous measurements, they sort of concluded that they had some peak corresponding to magnetic ordering. There was, in fact, our colleagues also did a second type of experiments on these samples, in fact, considering the thin films, which was μSR. And in μSR, what we know that this type of experiments, you basically implant polarized muons in your sample, and then you look at the decay of these muons by emitting positrons, and by measuring these positrons, depending on which direction you measure them, then you are getting information about the polarization in the system. And the asymmetry in this decay is usually the one that gives you information of the polarization, because you measure basically some asymmetry in this decay. And here what I'm showing is this asymmetry as a function of the time of the decay of the positrons as a function of temperature. And basically this asymmetry, there is no, it's within the error bars, there is almost no asymmetry being observed. And moreover, by looking at the Larmor precession of the muons in the applied field as a function of temperature, basically there is also no change in the Larmor precession. If there was magnetism in the sample, that's what one would observe, that one would observe basically this change of the Larmor precession. So the conclusion is that all these samples, they don't show long-range magnetic order. So there is no magnetism. Then we also did calculations for these muon data in order to identify, to be sure that what they are observing is what they are observing. So what one can do in density functional theory calculations, you can identify the possible stopping sites of the muons by looking at basically the largest negative potential in your sample, in your unit cell, which is where you are going to expect that the muon is going to stop. So basically, this is a map of the different potentials in the unit cell, and therefore we can identify the region where the muon is going to stop, and we also can analyze whether there will be diffusion of muons or not. And what we find is that the muons actually stay rather fixed in these positions in between the rutheniums. And in the calculation also, we don't observe detection of magnetic moments. So we come now to the conclusion, okay, maybe there is indeed difference between the different samples. If you have very good samples, ruthenium dioxide doesn't order, so there is no magnetism. But let's look at then at these doped samples, whether there is some emergence of magnetism coming from the doping, as these VCA type of calculations were suggesting. So in fact, there are some recent experiments by Wang and collaborators on chromium dope ruthenium dioxide, where they observe, so here is again the Hall effect as a function of magnetization, and they observed some anomalous, in fact, an important zero field anomalous Hall effect that they attribute to the magnetism of the sample and to altermagnetism. And this, in fact, would correspond to what we were observing in our BCA calculations, that if you dope the sample, you are going to expect some magnetism of the altermagnetic type, as also these total energy calculations show. But, and here is the but, because one has to be very careful in this type of calculations, because as I was mentioning to you, these are virtual crystal approximations where what we do is that we substitute the rutheniums by other atoms that have exactly the dope charge that we want. So it's a type of mean field type of way of considering this doping. So in fact, what Andrew did now in more detail is, let's do a better calculation than that. Let's do indeed supercell calculations where we are going to consider this doping effect as it is in the sample. So basically as doped samples. And what is interesting is when you do this, and Andrew was doing, in fact, very large supercell calculations where you consider different type of concentration of chromium. What I'm showing here is then you can really analyze where is the magnetism in the sample. And what I'm showing is the magnetism. This is for different sizes of the supercells is that the magnetism in the samples comes always from the chromium. Here, these are the chromiums at 2 and -2. And this is the magnetism of ruthenium, which is just 0. So ruthenium doesn't acquire magnetic moment. It's the chromium that induces this magnetism, or basically that is the one that gives the magnetism observed in this anomalous Hall effect. And this is also, in fact, the result of this type of calculations, that what happens is that you have in this in this crystal some clustering of the chromiums, and they produce this observed magnetism. And ruthenium remains non-magnetic. So there was also the question, well, clearly it seems that if you have in bulk material, ruthenium doesn't magnetize, so is non-magnetic ruthenium dioxide, and also in thin films. The question is, what happens when you go to very thin films? So here we were talking about 10 nanometer thick films. So here there is this recent work by our colleagues in Würzburg, where they go to even thinner ruthenium dioxide films. So these are 3 nanometer films grown on ruthenium 001. And what is very interesting is then you start to really feel your substrate. And what they observe is that due to the mismatch with ruthenium 001, what they observe is a charge density wave. So a surface reconstruction due to the substrate and no magnetism. So collecting all these experimental and theoretical evidence, we come to the conclusion that ruthenium dioxide is not the best candidate for altermagnetism. We have very nice candidates, as Elena was showing to us, magnesium telluride or mangan 5 silicon 3, but not ruthenium dioxide. And with that, I come to my conclusions that I was trying to show to you by combining calculations, density functional theory calculations with mu-SR, neutron scattering experiments, and thermodynamics, that we come to the conclusion that ruthenium dioxide doesn't show long-range magnetic order. It has been observed in different samples by different groups in neutrons, mu-SR, and also in at least 10 to 11 nano thin films. Also, what I have to say from the theoretical side is that there is, from all the metallic magnets that we know, there is no case that we know where DFT is not predicting magnetism. Usually, density functional theory calculations tend to predict more than less magnetism. So in fact, the tendency to magnetism is overestimated in a DFT calculation. So if the DFT calculation already is showing that magnetism is not favored, this is telling us that, in fact, the system is non-magnetic. So ruthenium dioxide is a very good metal, and it's not magnetic. And the dope samples, it seems to, in fact, the magnetism come from more from the doped than from having the magnetism in the ruthenium. So with that, I come to my these are my conclusions. And I thank you for your attention. I think that ruthenium dioxide has been an extremely important example to understand the concept of altermagnetism, but unfortunately, the system seems not to be magnetic. And I thank you for your attention.
So, any questions to this talk? Yes, Jeroen?
So thank you for a very nice talk, Jose. I think there's a recent report on ultra-fast optics on ruthenium dioxide films, and maybe you know. So I think their interpretation is that there is still some magnetism. What's your take on that?
That's the question. I think that's the point that I was trying to make with the thin films, because in the thin films one has to think: do you have some kind of reconstruction, surface reconstruction? Depending, I mean, this is now what I must admit that I don't know these experiments you're mentioning. But the question is about the quality of the samples. Do you have there some vacancies that are influencing your measurements? I have to look at these measurements. I haven't seen them. I think there is where you really have to go into the detail, into the details of your samples, what you know about your samples. My point is that it's not at all robust. In ruthenium dioxide, it's not a robust property as you see in manganese telluride. It's definitely not.
Thank you. So there is a question online by Bernd Bischner.
Joe, hi Jose. Thank you very much for the nice talk. I fully agree that ruthenium oxide is not magnetic, and we had already this suspicion when we started working on that. On the other hand, there is a saturation of the Hall effect if you go to high magnetic fields, and that's also, let's say, also seen by us, and there's no question that it appears. So can you calculate that? Can you predict?
Yes, we are calculating that, and I cannot give you the answer yet, but more or less what we see is that it's the magnetic field is that you apply is extremely, it's basically, you see a lot of the effects of the magnetic field. I mean, we don't have the end of the calculations, but I think we can explain that. So we are working on that, Bernd, because this was one of the, I could sort of explain why the neutrons, what they were seeing, probably it was other effects, but I couldn't give you an answer about the anomalous Hall effect, and that's why we are now doing these calculations. And I think we can answer that, but we still have to finish the calculations. As soon as I know, I tell you.
Yeah.
Okay.
Okay, thank you so much. Let's thank you.